Varda's hat trick and Earth's twin Venus. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. In just about 2 years, Varda Space has launched 3 missions, each one launching and returning to our own planet successfully. From testing hypersonic travel to autonomous pharmaceutical research, Varda Space is working to make launching and recovering these capsules routine. We'll speak with Varda Space's Nick Ciadella about how the company hopes to make deliveries to and from low Earth orbit as common as shipping here on Earth. Then, often referred to as Earth's twin, the planet Venus has a lot in common with our own planet. But thanks to a new data analysis of decades-old research, the way scientists are thinking about Venus is changing. We'll speak with NASA's Justin Filiberto about new insight into Venus and what's ahead for upcoming missions to Earth's neighbor. That's ahead on Are We There Yet? Varda Space is 3-0. The commercial space company is sending, quote, huggable capsules into low Earth orbit for autonomous research and has returned its 3rd successful mission. The company's goal is to make inexpensive, efficient, and fast re-entry capsules, and hopefully one day have these capsules shipping and making deliveries in space just as we do here on Earth. Here to talk more about these capsules, the mission, and what the future holds for the company is Varda Space's Chief Technology Officer, Nick Ciadella. Nick, welcome to the show.
Thanks for having me.
All right, so Varda Space, 3 successful missions now. Congratulations. But before we get into that, give me the elevator pitch. What are you all working on?
Yeah, 3 successful missions, obviously been quite a ride. But yeah, at a very high level, so Varda is developing the first pharmaceutical manufacturing platform off our home planet. Long story short is this has been essentially proven on the International Space Station many times over the past few decades, but we're really trying to be the first company to commercialize this technology at scale. So we do that with cheap, fast, and reliable reentry capsules, and really advancing that technology into an autonomous state, unlike the International Space Station, where you have to have humans in the loop operating these processes. We run it with, robotics effectively from control on the ground.
Yeah, we talked about kind of the pharmaceutical breakthroughs that happen on the International Space Station. And you're right, there's human in the loop there. And we have spoken about the work that you do in creating that autonomy. But I mean, really, what is important is about getting this stuff back, right? Because medical data on the International Space Station usually utilizes a return capsule like Dragon, but you are creating kind of the lab in its own capsule, and then you have to bring that capsule back successfully to capitalize on what you've learned, right? How difficult is that?
It takes a lot of blood, sweat, and tears from a really talented team to get it there. But yeah, the big piece being that we leverage that autonomy in our spacecraft. And so the big challenge being, how do we get that capsule from orbit, from its manufacturing state in orbit, and how do we get it back in a routine and reliable way? So our key success metric is high cadence. How do we make it so that we can perform these pharmaceutical processes, crystallize these drugs in orbit, and then bring them back routinely so that shipping to space is just shipping?
What challenges are you facing or did you face when developing, these initial capsules? What do you have to think about in trying to return that stuff safely?
Well, there's a few things, and so we can kind of talk through them one by one. But the very first thing from a technology standpoint for a capsule is, how do you bring a capsule back from orbit and have it survive the heating environment? You're coming back over Mach 25 times the speed of sound, 7,000 plus meters per second if you live in those units. And how you do that is you're essentially hitting the atmosphere at those speeds. And so if you've ever had wind burn from skiing, it's, that on steroids. And so how do you put materials on your vehicle that allow you to survive that environment? The big piece there and, is really us standing on the shoulders of giants. Folks at NASA, specifically NASA Ames, have been incredible partners to us. And so for even the very first few missions, they actually supplied our heat shield for the vehicle. And since then, we've really grown that partnership so that they've, transferred that technology to Varda so we can vertically integrate, make that heat shield ourselves, and really improve on our cadence internally towards our ultimate goal. So that's kind of the first big thing that comes to mind. The other one is, and this one probably got a bit more news because our capsule was up in space a little bit longer than we wanted to on the very first one, was the challenges in regulatory and new policies. And so for our very first mission, not only were we bringing a new idea to market, but also we're incorporating that with new policy for how you do or do not bring, vehicles back or to space. So, we've been really building our partnership with the FAA and what that looks like towards how do we do this in a growing orbital economy.
Tell me a bit about the capsule itself. Right now, I am mesmerized by a video that you posted of the capsule reentry and watching the plasma. So I will admit I am a bit distracted right now watching this. But tell me a bit about the capsule itself. How big is it? What does it look like? And what does it have on board to help it meet its mission's goal?
So it's about 1 meter in diameter. So we like to say it's like a huggable size. And overall, it weighs about 90 kilograms. So it's like 190 or so pounds. Relatively small. But as far as bringing it when it comes back, it's designed such that it's passively stable. So it can be tumbling end over end, as you may have seen in the video that you're watching. But once it starts hitting the thick of the atmosphere, it passively rights itself so that the heat shield that should be forward is the one that's taking the brunt of the blow. So yeah, I don't know if you're and similarly, if I don't know if you're watching the most recent video, but sometimes it'll pick up a little bit of a roll. The most recent video allowed us to get a great video of the reentry environment while also with the Earth in the background. And so, as you can see, we have a camera on board so we can get cool reentry videos like that. But otherwise, internally, the system is really designed to be really, really quite simple. The capsule, once it's on a deorbit trajectory that's performed by the satellite bus, is, like I said, a passively stable vehicle. And effectively, it performs that portion of the reentry mission on a series of timers. In terms of, is it at the right place? Is it separating from the satellite bus? And is it ready to deploy the parachute? And that's sort of how like the sequence of events goes from space to the ground.
Is that satellite bus yours? Is it part of the mission, or are you renting space on it?
So the first few missions, we partnered with Rocket Lab and their Pioneer satellite bus. So that's been an incredible partnership for us, and really has gotten us to really get on our feet. And so they developed that spacecraft, both for their own commercial uses, but as well as for our initial missions. That's allowed us to really build off of that. And so the satellite bus is just us on top of it with the capsule, and that puts us on that return trajectory, and then we separate from the bus when we're on our way back.
Gotcha. So the capsule itself doesn't have any propulsion. The bus essentially throws it back to ground, right?
Exactly. Yeah. So the satellite bus has the onboard propulsion system that allows us to get back, and so they have their Curie thruster that performs the maneuver, and that's what puts us on the reentry trajectory.
So essentially, you're not just flinging these things into orbit and then they're coming down whenever they want to. You have some control over how much time they spend in space and where they come down.
Yeah, exactly. So they'll sit on orbit for, in general, we target a few weeks to a few months, and to perform the manufacturing portion of the mission. And then basically on our command, we'll do a series of burns, and those series of burns, ultimately lead into the deorbit trajectory. So it can last up there for effectively as long as we would like. But yeah, after that, then we determine when it's time to come back.
You mentioned that there's simplicity in this design, right? It's set to orient itself to hit the atmosphere correctly. There's no thrusters or propulsions on the capsule itself. That simplicity is by design, right? And that helps build up to this higher launch cadence, right? I mean, is that part of the whole thing? Is that you want to make these simple and cheap and be able to get them up as fast as you can?
Exactly. That's right on the money. The whole design intent going into the capsule and the reentry mission was really just to stay focused on what the ultimate goal is. Like I said, to be bringing these capsules back at high cadence and reliably. To do that, having a passively stable reentry capsule that's highly reliable and very simple allows it to be that cheap and fast vehicle that we need it to be. And so we can make a bunch of these without having to be, extremely capital intensive to bring back, vehicles, let's say like the size of Dragon.
And we should say not cheap in the sense that it's cheap, but inexpensive, right? Low cost,
Inexpensive. Yeah,
Um,
exactly.
so you've had three successful missions. Were these your first three missions? Are you 3-0 when it comes to?
We are 3-0.
That's pretty impressive.
Yeah, I'm excited to say that is the case. Yeah.
What have you learned from these three successful missions that are going into future iterations of these capsules?
A big piece of why, like I said, we're doing this is to really develop that pharmaceutical manufacturing platform. And so a couple of things that we've done over the past couple of missions is, one, really just building in, frankly, the habits and processes that allow us to bring a capsule back at all. We're only the third private company to really bring back a reentry vehicle in any respect, let alone being 3-0 in our first three missions. That's kind of like step one. And then step two really being, as we're flying each of these missions, we're really learning more about our pharmaceutical hardware that we're flying in the capsule, and we're iterating on it flight over flight. And so we're getting that data back from those crystals that we're making and understanding how the space environment does or does not impact, the drugs.
Finally, we mentioned at the start of the conversation, a lot of this pharmaceutical research and manufacturing is done on the International Space Station with the humans in the loop there. Findings are returned through other returning capsules. But, as NASA looks to retire the International Space Station in 2030 and hoping that commercial space stations come online to fill in the gap, knowing that there could be delays with that, I mean, where do you see your technology fitting in a post-ISS world?
I think Varda is the perfect platform for the post-International Space Station world. Ultimately, it's the thing we can get up there quickly, and we're actively operating today. And so if there is current research being done on the International Space Station, we can take that research that's being done today, maybe tweak it so that a human doesn't have to be in a loop slightly, but ultimately fly it this year. And so we can continue that research today into, our vehicle tomorrow. And so that's kind of like the key enabler, that, we don't have to have a human rated space station ready to go for us to really bridge that research gap between the International Space Station and the next time that a commercial space station is available. And so we can be that autonomous platform while not, risking human lives to continue that research.
And finally, you said you want to get up to a high cadence. Do you have a goal in mind? What will you consider a successful cadence?
That's a good question. So, we'll know we're successful when we're seeing, a shooting star or our capsules coming down every day. That's sort of the ultimate goal. When shipping from space is really just shipping. In the near term, that looks like steps towards that. And so really targeting things like one a month and growing to that. But that's kind of how we'll know when we're successful, is that anyone who wants to do research in microgravity can come to us, with an idea, fly on our platform and get their data back, in really short order. Today, that order takes 2-year wait times or longer. And so really being able to improve on that research and bring it to market commercially is what that looks like.
Well, on your way to that goal, congrats on the hat trick. Nick, thanks so much for joining us.
Appreciate it. Thanks for the time.
That was Varda Space's Chief Technology Officer, Nick Ciadella. Still to come, a glimpse into the world of Venus and what research and missions are coming to Earth's twin.
We want to know how planets evolve. We want to look in the past. Why did the Earth become habitable and have life thriving, whereas Venus, which is so similar in size and in composition, doesn't have life?
That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. The planet Venus has several similarities to Earth, including its density and composition. But even though it's often nicknamed Earth's twin, the planet didn't evolve like our planet at all. It's got a thick atmosphere. It's hot because that atmosphere traps greenhouse gases. And now new research shows that even Venus's crust is different from our own planet. After a fresh look at old data collected during a mission decades ago, scientists were able to determine that the planet's crust is unstable, breakable, and can even make lava. Plus, it opens up a new perspective on the planet's cycles. I spoke with Justin Filiberto, NASA's Deputy Division Chief of Astromaterials Research and Exploration, to talk about these new findings and discuss future missions to Venus and what questions those missions may answer. Justin, welcome to the show.
Thanks. Happy to be here.
Yeah, great to have you. And you've got some pretty interesting findings you recently published in a paper you co-authored. But before we get to that, I want to talk a bit about why Venus is so fascinating to planetary scientists and scientists like yourself. Why you study it in the first place?
That's a great question. Venus is very similar in size to the Earth. Its density is about the same as the Earth, and its composition is therefore about the same as the Earth. So in theories, Venus should be very Earth-like. It should have gone through a similar evolution, and yet it didn't. It has a very thick atmosphere. It is the surface is obscured by a thick, omnipresent cloud deck. The surface is at hundreds of degrees Celsius and 92 bars to the equivalent of ocean floor depths, and has a very caustic atmosphere. And so it's intriguing because it's not the Earth, yet it should be.
And do we have any idea why?
It's one of the things we're trying to figure out, and we're getting ready to send missions back to Venus in the upcoming decade of Venus exploration to look back in the history of Venus and figure out why it took a very different path than the Earth.
For a long time, Venus has been considered geologically stagnant, but that is not the case according to some a new analysis that you helped with, right? Can you tell me about what these findings have shown about Venus and how it's changed the way scientists have thought about the planet?
Yeah, so I'll go back to the Earth for a second. On the Earth, we have something called plate tectonics, where our plates are moving against each other. And when two plates collide, the denser one subducts and brings material back into the interior of the Earth. And it means that the Earth does not have a rock record through all of its history. And so we can't get a very early history of Earth just looking at the rocks. For Venus, we don't have evidence of subduction zones. We don't have a Mount St. Helens. We don't have other volcanic belts that look like that. And so the thought was that Venus through time would get a thicker and thicker crust where lava would come out and it would just make the crust thicker, and Venus would cool and just have this stagnant one-plate planet. What our new results show is that this isn't the case, that as the crust becomes thicker, because Venus is so hot, that crust becomes unstable, and either the bottom of the crust breaks off and goes back into the planet's interior, or gets so hot that it remelts and makes lava and can cause eruptions.
How did you come to this conclusion?
So we took our best evidence for the chemistry of rocks on Venus from the Venera and Vega probes from the Russians. And we used geochemical modeling to look at, okay, if we go down into the crust, what would those rocks mineralogically look like with depth? And what we noticed was when we calculated the density of those rocks, at some point they became so dense that they were denser than the interior, or they were melting because they were just getting too hot.
That's pretty fascinating. I'm reading about this, and the modeling that this paper used, it determined the crust is about 25 miles thick. How does that compare to Earth's crust?
So the crust that we stand on, our continents, are much thicker than that. They're granite. They're much more buoyant. That's much more like our ocean floor crustal thicknesses.
That's pretty wild. Let me talk about where this data comes from. When was the last time we've sent a probe to Venus to gather these measurements?
So the data we're using is from the Russian Venera and Vega, so it is decades old. NASA hasn't sent a Venus-focused mission in decades. This is all going to change. NASA has selected the Da Vinci mission, which is an atmospheric probe. We're going to come down over Alpha Regio, which is a tessera. So this area that we think may be like our Earth's crust and our thickened crust. And NASA has also selected Veritas, which is going to be an orbiter, and it's going to go look at the volcanoes. It's going to figure out how thick the crust actually is and look for evidence for volcanic eruptions. And then ESA has also selected the Envision mission, which again is going to be an orbiter looking at high-resolution detail of the surface of Venus.
We'll talk a bit about those missions and what you hope they uncover for your particular area of expertise in a bit. But I want to go back to the fact that this is decades old data. Was it just a matter of, you and your team picking up this data and getting curious and looking into kind of the crust of this, or has technology advanced? Has modeling, computing power changed that's given new light to this data? How did you come across these new findings with data that's decades old?
Yeah, it's a little bit of all of that. We ask better questions as we go through time, and our tools get better through time. And this study actually started out as an intern project for an undergrad summer intern who was working with us. And we said, hey, let's use these new models and see what the interior or what the crust of Venus would look like. He started doing the models. He showed us the results, and we're like, wow, this is really cool and more interesting than just an intern project. And so we developed the project even farther.
I love that, how it was just a little bit of curiosity and some older data, and you come to a new conclusion. That's really cool. So tell me a bit about, you said that there is, with Earth, we don't have much of a record, a geological record. That's not the case for Venus, right? How can we tap into that geological record and see what was there?
So Alpha Regio, where Da Vinci is going to come through, is a region called tessera, which means sort of tortured terrain. It looks like it's thicker crust that has gone through a lot of geologic processes, and it's thought to be the ancient crust of Venus that's 4 billion years or older. And so Da Vinci is an atmospheric probe. We're going to measure the chemistry of the atmosphere. But for me as a geologist, the thing that excites me is we're going to get images of these rocks as we come below the cloud deck and actually image at different heights through the atmosphere and get sort of narrowing in on closer and closer pictures of these rocks and be able to tell what they are.
Have scientists like yourself ever gotten pictures like that of Venus?
So the Venera and Vega probes, so going back to those Russian missions, did take images. They landed on basalt and lava flows, which is really cool. The rocks look reddish in their images, which means that they're slightly weathered. So we know there's chemical weathering going on. We see dusty material, so we know there's fines and processes that can break rocks apart going on. But we don't have images like that of the ancient rocks.
Do you expect to find any evidence of life or water or anything like that? I mean, this is Earth's twin. What might we find on Venus?
So we know water is not stable on the surface. It's too hot. It's too caustic. However, there is some amount of water in the atmosphere. And so with Da Vinci, we are going to look for how much water is there. We're going to look at what the gas composition is, what are the clouds made of, and figure all of that. We are not expecting to find life. The surface of Venus is, as you said, hellish. It's well outside the conditions known for life on Earth.
So then, with that said, make the case for Venus. Why study it? Why are we sending these probes in the first place?
Because we want to know how planets evolve. We want to look in the past. Why did the Earth become habitable and have life thriving, whereas Venus, which is so similar in size and in composition, doesn't have life? As we look at other planets, they can tell us about what happened early in the Earth's evolution that got us to where we are today.
And as you mentioned, some of those places, you're looking billions of years into the past. So finally, Justin, these new missions coming online very, very soon. The first missions in decades that are they're going there. You've made the case for it, but what are some unanswered questions that you still have as a geologist, as a planetary scientist, that you hope that these missions will help answer in the coming years?
Two big questions that I'm really excited for. One is our landing site, alpha ratio. Is it granite? Like our crust on the Earth. And that tells us that Venus, early in its history, had water, was more habitable, had a very different environment than it does today, and something drastically went wrong. Or is Tessera just altered basalt, and it was always this hellish environment? The other question is, Venus is covered in huge volcanoes all over its surface. Considering its size and it's similar to the Earth, those should be active, or there should be active volcanism somewhere. I want to know, and one of the big questions that I want answered is, are there volcanic eruptions on Venus today? And if so, how many, and where are they?
I'm thinking back to my high school earth science class here, so forgive me if I'm getting this wrong, but can you have volcanoes without tectonic activity? How do these volcanoes form differently than they do on Earth?
On Earth, volcanism happens at plate boundaries like subduction zones and Mount St. Helens, where one crust gets subducted, it releases water. The water is what sort of drives the mantle to melt and produce these very, very explosive eruptions. But we also have volcanoes not associated with plate boundaries. So things like Hawaii, where we've got excess heat in the interior, that heat causes melting and it causes a hotspot volcanism. That's what we think there should be on Venus.
Hotspot volcanisms, hellish planets, landing in granite. It sounds like a really, really awesome mission. So we're very excited to find out what's next for Venus and some pretty incredible findings from 30-year-old data. That was Justin Filiberto, NASA's Deputy Division Chief of Astromaterials Research and Exploration. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on the Central Florida Public Media app, NPR's app, Apple Podcasts, Spotify, really wherever you get your podcasts, including YouTube. Stay connected with the show. Follow us on social media. We're at AWTY Space on Instagram and Facebook. And if you've got an idea for a future episode of this show, or you want to join us as a guest, shoot us an email. It's arewethereyet@cfpublic.org. You can find more space coverage online, cfpublic.org/space. Are We There Yet is a production of Central Florida Public Media. Our intern is Ashley Reed. Our producer is Marian Summerall. Editorial guidance from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.